Okay, our next speaker is Manish Tiwari from UCL Engineering, and he's talking about surfaces for icing and impact. Please go ahead.
Thank you, Frank. Well, first of all, thank you very much to all of the organizers for inviting me to join. And I would like to start with an apology for not being able to join the whole workshop, actually. I have a few excuses like the rest of the people who I'm not being able to make. So when I was preparing this, so I was fortunate enough to be invited for the previous two workshops as well. And at that time, and on this occasion, I was thinking, what do I have to say to the sea ice community? And the answer ranged from nothing to really nothing. But then I thought about it, and I thought that, okay, if, like Ian did this morning, if we try to give you a bit of an overview of how we approach the problem of icing, and particularly how it relates to icing and formation of ice on solid surfaces, or mitigation of ice, or easy removal of ice, etc., it might have some relevance. And one of the things that I picked up in the few talks I attended yesterday in Alto's presentation was this idea of interfacial properties and so on. And that resonates with me. And I asked, and probably bothered him enough about some questions related to that. And it'll become clear as to why I was thinking. So I am an engineer. You probably will meet people approaching the problem of icing, even in the engineering community, with slightly different set of perspectives, perhaps. But hopefully, I'll give you some insights into how we actually approach this problem. And what I want to focus on, as I said, is the idea of icing and impact. In particular, this is relevant for things like aerospace industry and applications of that nature, where the problem of impact and icing tend to be interconnected. And then this is my way, the question mark here is my way of basically making myself irrelevant to my community. And I'm not trying to be extra modest there. It will become apparent. Because we are thinking about, ice formation on a surface, we are necessarily thinking about interfaces. And for the last few years now, I've been thinking about, is it all about interfaces? Because at least in our community, it has been like that, or thought through like that. But it's beginning to change. And so I'd like to summarize some of it, and I'll let you decide what you think about it. I didn't want to add nano here because I felt that I would really lose my audience if I haven't already. But that's what we are doing. A lot of the work is at small scale and so on. So I appreciate that it's a far cry from the kind of length scales, etc., that we have been talking about probably for a majority of the talks, right? But nano is important. That bit I hope to be able to communicate. So let's see how we get on. So because I tend to talk, and it's very useful to have that clock over there, because otherwise I'll just go over time, and I don't want to do that. I realize that I'm the last talk, and a lot of the student members and research fellow members in the audience have confessed to me how the energy level is going down. It tends to happen. So hopefully, bear with us for, I don't know, another 35 minutes or so, and then it'll be done. So this is my team. Well, I should say our team, because there's a lot of collaborators and a lot of these people are shared, and we're fortunate enough to work with them. This is pre-pandemic, so some of the names have changed. And most of the work is done by them, so it's only fair that I acknowledge them. From this, Nat is in the audience. He looks different, so do I, because it has been a few years. And of course, a debt of gratitude to the funders who have made a lot of the work possible. So, as I mentioned, I want to talk about surfaces which make it hard for ice to form, or if it forms, make it easy for us to remove them, right? And problems associated with that. And so this passive / energy efficient way of managing the problem of icing is what we have been thinking about now for, I think, about a decade now. So obviously, this is a problem that you are all very well familiar with. At least I don't have to talk about the importance of icing. And I'm hoping that we pick up few commonalities across these different disciplines that might be useful to bring it back to Shasha's point about, are there open questions, et cetera, et cetera. So I'll have a few for you to think about or not going forward. So how we approach this problem. Am I audible, by the way? I have to teach next week, so I'm practicing this week. In aerospace community, because of relevance to the cloud and droplets, etc., the icing problem is very intimately related to droplets on surfaces, right? And that's how I came to this. And I was working on these surfaces which you can engineer through surface texturing and engineering surfaces, etc., to change their wetting properties. And so you can make them very hydrophilic, so water loving, very hydrophobic, which is called superhydrophobic, and so on. And we can use this sort of an angle measurement, which is higher up at the front, if you think of an inclined gray surface here, and slightly lower at the back. There are surfaces where the droplets just stick, but if we design them right, we can make them slide. And so the difference between these two is a qualitative measure of the stickiness of the droplet. And so there was a paper, just slightly over a decade ago now, which talked about correlation between these two problems. So adhesion of liquid and ice on a surface. And they showed that it correlates very well with this, what is called receding contact angle, this interface angle with the surface here. And so people thought, including myself, okay, if we're fairly good at making these surfaces and increasing these contact angles, etc., so we will have a surface that will reduce ice adhesion. Just the way I posed or I talked about it, you probably can guess that it didn't turn out that way, or not as simple anyway. But there was a correlation between these two problems, so that is not to be denied, of course. And the implications were quite strong. So, as I mentioned, we were, designing this kind of surfaces. So you're looking at an electron microscopy image of a surface that we were able to make, which are a collection of nanoparticles, etc. Essentially, we are engineering the surface texture. And the inspiration for this comes from nature. So this is an example that is fairly well known on non-wetting surfaces. So this is lotus leaf. And just through evolution, this surface has evolved to have a very complex hierarchical morphology. So surface morphology which has micron scale bumps, and if you zoom in, you actually see tubes, nanotubes, I should say, made out of wax. And so it makes it very difficult for water droplet to stay on lotus leaf, which gives it its so-called self-cleaning behavior. So this is what we were doing. And as I said, we thought that if the droplet does not have enough time to sit on the surface, even if it freezes, it will go off the surface, right? So we can at least mitigate the problem, if that makes sense. Okay. So this was an academic lab, and unlike Ian at the time, we didn't have access to large icing wind tunnels where you simulate conditions that would be practical. So we built one in-house, fairly small one. We're looking at about, this whole box is about 0.5 meter wide and so on. And the neat thing was it could allow us to controllably observe droplets as they were freezing. And I won't go into fluid mechanics of this. I want to make it to a different point. So these are the first set of experiments we ran, and I've talked about this before. So if you are aware of this, please bear with me for a few minutes, and then I'll bring it to the point that I want to make. So what you observe if you put these kind of droplets on, let's say, surfaces where the droplet beads up, like it does on a superhydrophobic surface, so-called. You see, first of all, that in this case here, this is so-called heterogeneous nucleation of ice, which means that the ice starts to form at the interface. This is a cold droplet. We took pains to make sure that it was cold. And this is the same experiment. On the right, we have a little bit of gas flow. Okay? And what we see is that nucleation happens up here, in the liquid, that is, right? And so that means we have completely switched the nucleation mechanism. Okay, so that gives us a paper. The implications are actually worse than that. What it means is you're taking out the surface from the picture, the substrate from the picture. So if you're trying to design the surface to stop this nucleation from happening or to reduce icing, etc., you've lost the battle before it starts, just because you have a bit of airflow. Okay, so that takes us a little bit away from the interface. And the next question was, well, why is this happening, right? And the reason this is happening is you have a bit of evaporation because of the gas flow. And so that makes the top of the droplet a little bit colder. So it's like sweating, effectively. So we did a lot of work here to prove that it was indeed that, and so on, and controlled experiments and what have you. If you're interested, we can go into that. So that means that we do need to think a little bit away from the surface. You know, the surrounding conditions are important, right? Okay, we could have guessed that, I suppose, right? If we have an undergraduate student we are trying to get into this field, and if we ask them, do you think only the surface matters? They will probably tell you, no, everything should matter, right? So there's nothing dramatic going on. Okay, so let's see how the freezing process actually looks like. So what happens is, if you have a cold droplet, you know, it is in a metastable state, and if we put a little thermocouple inside of the droplet, and we try to measure the temperature just to monitor the freezing process, right? And the humidity outside is dry. And so what you see is you maintain there, eventually there's this thing called recoalescence, so sudden nucleation, followed by a thermally controlled freezing process. And so the point is that if you have this first step, the second step is definitely going to happen, and the second step is what is referred as Stefan's mode of freezing, which is heat transfer controlled. I don't know if you can actually see, there is a bit of brightness here, right? And it caught our attention because I talked about evaporation before, right? And we were doing these experiments, you know, you're looking at one out of, I don't know, thousands of experiments that we did, and it was very reproducible, right? What's happening here is you're probably looking at some condensate formation, meaning tiny droplets appearing. And the reason for this is this evaporation creates the vapor, but we have cold chamber, right? So that vapor cannot stay as vapor, so it condenses around. And where does it condense? It condenses next to the droplet. So we took this a bit further, and now I will really bring it away from the interface. So now I have this droplet, and we are now looking at it with microscope. So this is our so-called big droplet now. Millimeter droplet has become quite big. And I'm going to show you around this droplet for two different substrates. This is a plastic, this is a copper metal. And let's see what we see. And this is endlessly reproducible. There's nothing dramatic going on here, right? And let me play this one too. So on metal, we see some formation, but it dries out. On the plastic substrate, we have almost like an extension of the droplet that freezes. And the reason for this is time. And the reason for that is the rate at which heat can leak through the substrate. Because when we freeze, we release the heat. If you have conducting substrate, the heat loses. So you have less evaporation, right? You see, it's completely away from the substrate now, from the interface now, right? This is governed by the substrate thermal conductivity, right? And obviously, I won't be showing it to you if there was no implication, right? So you can actually now show that, if this freezes, the ring around that touches the next one, causes the freezing of the next droplet, and next one, and so on and so forth. So there is almost like a chain reaction in the freezing process in dry situation when the humidity is low, as long as the evaporation takes place. Okay. So that is, I suppose, one thing to keep in mind, and it is taking us away from the interface, right? So the next question is, so shall we just give up on the design of ice-phobic surfaces? And if we want to start, where do we want to start? So we went back to this idea of nature and so on. Among some of the limitations that I've been touching on in this nature inspiration, the fact that none of these are designed, natural surfaces are designed to survive in cold, harsh conditions. Some of them are, like polar bears are, for example. And we can talk about how polar bears are different. I want to stick to time. But the main point, I mean, these are beautiful structures, right? You have structural colors, you have, insects here that even bacteria cannot grow on, and so on. So these are pretty powerful evolutionary structures. But they are not designed for low temperature. So what can we do so that we can maintain this kind of low adhesion, but go towards extremes of temperature, right? Lower temperature and so on and so forth. What comes out of all of this is, and I'm skipping a few things just for the sake of time here, this complicated morphology that we see from nature, it does give us drop mobility, meaning the droplets have hard time sticking. But as we have seen, just the mobility of the droplet on the surface, which is due to the interfacial interaction, and we can actually engineer that interfacial interaction to extremes, actually, right? And our group is not the only one. There are groups all over the world who are doing that. The difficulty with that is when we go to icing, we need this low thermal resistance, right? So the heat has to be able to conduct away. We saw an aspect related to that. And this is the bigger one that the engineers actually worry about, because if you form this kind of surface treatment, how long are they going to last? Ian talked about that, right? He has not seen any coating, he said, that lasts for more than 10 minutes or something like that. So we can't just get rid of all of this. And so far, we have talked about nucleation process. And if the question is, can we control nucleation? The next question is, well, how precise do you need to be with your surface preparation to be able to control nucleation? Okay, there's a few problems, I guess we can tell, right? And oftentimes, we end up having to have a bit of trade-off around these multiple issues. So I'm going to skip all of this. You'll probably read this in a summary perspective article sometime soon. So what we see is, if we are serious about controlling the phase change process itself, not only do we need to worry about the control of this adhesion between the droplet to the surface, we also need to be extremely precise with the surface texture. And the reason for that is you are effectively trying to mess about with heterogeneous nucleation. This liquid is in a cold state, right? The droplet is cold and it wants to freeze, and you don't want that to happen. And for that not to happen, your roughness scale better be down to the size of an individual embryo. And you don't have to take my word for it. Just plug in some numbers or properties. This is surface energy. This is volumetric free energy, Gibbs free energy. Plug those numbers in. You will get a number something like that. So this is a problem that is begging you to do nanotechnology. Okay? It is literally, it's there in, this is, if we were teaching a course in how ice forms, this is where we will start. We should start, right? Okay, and if anything, it is worse with the heterogeneous nucleation, etc., etc. So far what we see is, okay, substrate properties are important, but being precise at the interface seems also to be relevant. Okay, let's keep moving. So we did that, and I showed this in my presentation a few years back. This is an old piece of work. So if you actually, design these kind of pillars, and on top of the pillars you make really precise nanostructures, you can actually delay formation of ice. These are actual experiments, by the way. This is about a day, right, at minus 20 degrees centigrade. You can delay ice formation for a day. It's far cry from being able to do that on these structures, right? Because we haven't talked about contamination, we haven't talked about other robustness issues, etc., etc., etc. So the first thing we did was to think about, well, how can we scale this up? How can we do this on large surfaces? So we spent quite a lot of time doing anodization of metals and things like that, things that people in industry use quite commonly. And we had limited success with that. The difficulty that this approach still leaves us is the second aspect of designing surfaces for ice solidity. And that has to do with this. And Frank was talking about this actually, which is, as I said, we have the impact problem to worry about as well. So now you're making very fine structures, right? And here comes a droplet, hits you at hundreds of meters per second, and all the precision goes away, right? Okay, so what do we do about that? Okay, so let's talk about it. Okay, so we obviously have been working on this for a while, and the thinking is, how can we design these surfaces now to be able to take impact resistance? This is nothing. This looks quite cool, and this is your rain droplet. In an aerospace application, we have hundreds of meters per second. But that's where we had to start, really, right? So I'm going to skip over a few things, and if you're interested, we can talk about this in detail here. So if you think about now a droplet hitting on a surface, essentially whether the droplet is going to cause any damage or it's going to get stuck on the surface or not boils down to balance of some pressures, right? And what you see is pressures that come about due to compressibility effect. So it could be the compressibility of the air that needs to drain out for the droplet to come down. Or if the speed is really high, you have liquid compressibility that comes about, right? So this is where your rain droplet is. And I'm not going to pretend even to go and talk about these parameters. We'll see. It's not relevant, actually, for what I wanted to share. And of course, there is the Bernoulli pressures. This rho is density, v is the velocity. So this is our so-called mind the gap problem. And the resistance here, because we are talking about textured surfaces, comes from the surface tension, right? Or the surface energy part. So if you can make these rough features very close to each other, essentially you are making it harder for the droplet to penetrate. And if you're making it harder for it to penetrate, the droplet will not get stuck. That's the thought process. So a lot of the so-called engineering happens on how can we make these pillars close together while maintaining all of the things that we have been looking at from before. And that is indeed near the interface, right? Because we are still talking about texturing of the surface. This has got almost nothing to do with that. The actual pressures that are forming, which are making the droplet go into the surface. What is this here? So essentially this is, I mean, it's also referred as water hammer pressure. So when a liquid is impacting on the surface, due to compressibility effect, you have pressure peaks forming. That's what I'm referring to there, right? And they just happen to dominate over the kinetic pressure or kinetic energy, depending on the perspective that you have here. And that's what I'm trying to show with these arrows here. Okay, so the one approach here would be that you make these pillars very close to each other and make them quite long, so that even if this droplet meniscus gets into the surface texture, it's not able to go down to the bottom, and it can use its energy back to recoil out. And so that's what this paper was about. And I'm not going to bore you, don't worry, with all of this fabrication process, etc., etc. It was led by Professor Papakonstantinou team, who's a professor in electrical engineering department. Now the difficulty here is I still have not addressed the problem of these nanostructures are still weak mechanically, right? Very basic problem. So what we were doing here is this was done on a glass surface. So it could potentially work on windows, for example, right? Windows as in building windows, not talking about aircraft windows. Those will be different. Okay, so I think we're still learning, right? So it's not like we should give up on the interfaces, but we need a bit more. And so for this, I'm going to go back to butterflies that I showed you earlier, right? Butterflies are cool for many reasons. One of the reasons is, if you try to touch them, you will break their wings. It's very fragile. But these things survive in Brazilian rainforest, right? And they can take rain droplets that are several millimeters coming at 10 meters per second. If you calculate the pressure that gets generated due to impacts like that on a flat surface, those should not survive. Okay? So what they do is what I'm going to show you, and this is thanks to a group from Zurich. This part is not our work. What they did is a very simple experiment. They took some butterflies, they put some of the wings on a flat surface, so supported, and some they let flex. And I'll let you watch. Over here, this will be a video. Free and supported. The droplet almost bounces off the free one. And on the right, it shatters. You're creating a lot higher pressure locally. Okay, so when we jump onto the sand, we don't feel the pain as we do when we jump onto the concrete. That's engineers' way of thinking. I know it's very hard. So we took that a step forward. I mean, you know, you can look at that paper. They have done it with many species and so on and so forth. Long story short, there's nothing special about butterflies itself, right? I was showing you all these microstructures and so on in the beginning. This mechanical property is also important. So we thought we can use that. And so to do that, so this becomes a way for us to go from the opposite direction. So rather than actually doing anything on the surface, you're now manipulating the pressure peaks that form as the droplet is approaching your surface, right? Okay, so that's why I'll bring it to this so-called water hammer effect, compressible pressure formation. And what you see here is there's a fair amount of debate about what the constants, etc., should be. I wish I could tell you I care. I don't. What I do care about is what I can control. And what you can control is what you're making your surface out of. That you can do, right? So what you have is the liquid, which is water. Not much you can do about that. But you can control quite a lot on the substrate. And so this Z factor here is so-called acoustic impedance. And effectively, these are two resistors coming together, okay? And so the effective impedance is governed by the two of them being in series. And so if you plot this normalized value of effective impedance, and you see that for a rigid substrate, you get a very high factor. That means the pressure peaks you're going to form are going to be high, whereas for flexible ones, you can reduce them quite a bit. So we took this a step forward, and we made a coating surface where we made the coating to be very flexible. So this is a paper. The chai is going to open up in a bit, which has been coated with one of our flexible coatings. I realize I'm skipping a few steps about exactly what the coating is made of. It's not important. Let's look at the principles. We'll think about what it's made of. And we can't afford good paper in UCL. That's why we have to use, torn paper. There's no finesse here, right? I mean, when it works, it works. And he's just going to try to crumple it a few times to try and show that, okay, there is flexibility, or this material can sag when you are impacting things on it. I'm going to skip that because I want to show you a couple of things. So then we ran our experiments, and you can now start to push the impact speeds to the point that in the way we do these droplet impact experiments in the lab is we release the droplet from a height, and the maximum speed you can reach is basically governed by the terminal velocity. So that's why you can essentially reach a rain droplet impact speeds 5-10 meters per second. So the step beyond that is to use jets if you cannot afford hundreds of thousands of pounds to do these tests in icing wind tunnel. So this is your normal car wash, basically, onto the surface to try and show that there is robustness here. And so what we are gaining here is, yes, we maintain the texture bit, but we have the flexibility of the material, which is reducing the amount of pressure that you generate, right? Okay, I'll keep moving. So Nat is in the audience. When I was here last time, I probably begged everybody to look about, flexible surfaces, etc., etc. Frank was kind enough to listen, and Nat was crazy enough to take this as for his PhD. So he's now done some calculations with 2D droplets by coupling fluid structure interactions here through asymptotic approximations. And what you can see here, I mean, this is the bit that matters to me a whole lot more than the other part. You actually, if you go from rigid to the flexible substrates, you can reduce the pressure quite a bit. And if you have viscoelastic materials, you have a bit of dispersion of energy around the pressure peak, so your pressure peaks broaden. Yeah, I'm talking qualitatively. If you are interested to be specific, either talk to Nat or we can talk about it afterwards as well. There are other, let's say, related things that you would expect happen as well. So typically in droplet impact, underneath the droplet, there is an air bubble that gets trapped, depending on the geometry. And if you have flexible substrate, you have bigger bubbles because the deformation is more. That tells you that cushioning is happening. That tells you that the pressure peak should be lower, right? And if you ask me, have you done one-to-one matching of the pressure that you measure in experiments and that you are predicting here with the model? No, we haven't. We're setting up the setup to be able to do that because we really need pressure sensors that are spatially resolved and have the time constants that you have here, which would be sub-milliseconds easily. Yeah. I mean, there's a lot to do here. Is all I'm trying to say. Okay, so far what we have seen is, I have a few minutes I want to show you. So now, if you are not bored yet, I'm about to bore you. Okay, so be ready. You're going to see some chemistry now. So what we have seen so far, okay, substrate properties seem to matter just as much as the interfacial properties. I think that we can agree, and we see that over and over. And I've shown you two examples. I've shown you the substrate mechanical property, right? And I've shown you thermal conductivity and so on. But should we then completely give up on this idea of texture precision? Or is there a way that we could maintain what we have learned about on the mechanical or the thermal side of things and still be precise? Okay? And so for that, we did this. This is now very fresh work, going back 2 years, 2.5 years or so. And so for this, what we are trying to do is we are using what are called metal organic frameworks. So these are our MOFs for short. So basically, I'm not a chemist, so I'm not going to torture you, don't worry. Essentially, you get a porous structure that is really, really fine, and it can be grown onto the substrate, which means that you can scale it up, which as an engineer I like, right? And it has the precision that can be as good as sub-nanometer, right? Okay, but is it still not going to be fragile? Well, every substrate has nanometric size objects, molecules, right? So we're not going to get around that. But these give us a rigid structure which are precise down to sub-nanometers. And we can grow them to very, very thin layers, which means that you don't interfere with the basic property of the substrate underneath. Does that make sense? So if I am just, let's say tens of nanometers thick, I have the substrate precision and it is really anchored onto the substrate. That's the idea, okay? Don't buy it yet. That's the idea. Then we can benefit from the underlying substrate. We can benefit from the heat being able to literally leak through and so on, yeah? So I'm going to skip this one because this is the chemist's way of teaching us that, okay, this can be really, really precise and so on. So we did that. And so we grew these so-called MOF layers onto substrates. And if you're really interested what they are and so on, we can talk about that. I'm not going to talk about this. This is a major issue in coatings industry. We have been using fluorines from non-stick cookware to clothing. And turns out that's not good. We need to get rid of these from carpets and things like that. One of the benefits, we didn't expect this, one of the benefits that came out of this is surface texture precision, and even oil contamination, etc., can be removed here. I don't want to talk about this. I want to go back and talk about this a little bit. So what you get is what you would expect, or you should expect, which is these layers are very thin and they are porous, which means that they are not able to scatter light, which means they are optically transparent. Right? So it's almost like, it's an added benefit that you get, right? And as you can see, we can maintain the properties that we have been talking about so far. Yeah? What about the proof in the pudding? What about the icing? Have we forgotten about that? If we have forgotten about that, then it's a wrong talk. So it does give us actually good things. So these are your control substrate. So now I'm showing you adhesion measurement, and I won't show you exactly how we do it and so on. And this is our so-called MOF coatings. So this is now down to a point where if the ice forms, if you are roughly about below 10 kilopascal, if the ice forms, you tilt it, it should fall off. That's what 10 kilopascal is, if you basic calculation from ice density being close to 1 and that sort of stuff. And it can last for, let's say, a few cycles and so on and so forth. And I have a few versions of this that I can go on and on and on. Okay, so let's see, does it work? Yeah, so what I have been showing you so far is for phase change control, there is no way around surface texture precision. We cannot get rid of that because it's there in the physics. But there are a few things we can do by choosing appropriate substrates, or by designing the substrates appropriately, or by making thick coatings which are flexible and thermally conducting, etc., with the top layer being precise so that you can interfere really with the nucleation process. And it can be extended using some, I wouldn't classify MOFs as exotic. They were discovered in late 90s in Berkeley. They're used in catalysis and things like that quite a lot. We have been really pushing to use them for surface engineering side of things, and that's why you saw what you saw. So the last point I want to make is what you don't see here so far is I have talked a little bit about this, right? The question mark there. So I've talked, surface texturing, nanoengineering, et cetera, is how we make our living in my team and with our collaborators and so on. But we do need to think about the bulk. And we do need to think about how we can alter the bulk materials, at least near the interface, to be able to get the best out of this kind of interface engineering. And I think this is where SheIce community might actually have a few things for us to benefit from, and for us to hopefully give it back, in the sense that how do we engineer a plank of steel near the interface, let's say a couple of 100 nanometers, so it gives you the kind of erosion protection, the fouling protection, the protection from the impact, et cetera, that you are running into. I don't know if we will have any answers in a couple of years. If you have ideas, please do share. There is a lot of open problems here, and I'll be looking at some postdocs. So if you have some good people who are working in these areas, or they think they can tackle some of this theoretically or experimentally, they will be more than welcome. Thank you very much. Everybody's gone to sleep, right?
Thank you, Manish. Nice talk. Very nice talk. Any questions, folks? Oh, Sasha?
Thank you very much. Thank you, Manish. Very nice. And I couldn't see that somebody slept. No, everybody was concentrated on your talk. There are several remarks. I believe there could be not many questions from others. So first of all, about acoustic impedance.
Yeah.
And there is just nearby Cavendish laboratory, and they studied it's a lot. And I believe Frank remember John Field, head of John Field, no? Okay, you're young for that. Okay. He was head of that laboratory, and they did a lot of experiments with elasticity, with elastic substrate.
Yeah.
But the problem with I understand that in your case, you are thinking not about elastic substrate as the uniform or isotropic material, but you are thinking about elastic cover.
Exactly.
Right,
yeah.
And this means it's much more complicated. So you have one layer of something, and on the top of it, thin layer of that elastic, and to kind of mitigate, is it right? To reduce the pressure, that elastic layer should be very flexible. Right. So it means that the properties are very different. And if the properties are very different, we return to this your question, where you said you're an engineer, about the interface. But now it's interface between two layers, and definitely it will be broken.
True.
Broken. True. So even you reduce that pressures, it doesn't matter, because all that pressure will go to that interface, and because of there is delamination, it's called, I believe, and after that it will be removed. So we return to that concern from the very first report.
True.
Yeah, and due to some reasons, about 3 years ago, we were asked to find conditions of substrate breaking, actually cracking by a droplet impact. So we did something like you showed, but we were studied that waves, compression waves, shear waves propagating because of the impact. But impact pressure were simplified, similar to yours, but it's not. It should be better, and kind of CFD should be involved in that. And we found, but it's people knew that well before us, that the main problem is not with the shear compression wave, but with the Faraday or Rayleigh waves on the surface. So it means the surface is most important. And if there is a crack or something on the surface, it grows.
It even concentrates that.
Yeah. So everything's there. So the point we concluded is that the surface should be perfect. So you should clean the surface first. They make material isotopic, and after that they clean the surface to polish it, to do something. And we concluded, but again, could be wrong because the sciences, go ahead. Sure. So that we should not put anything. Okay, not we. They should put nothing on the surface. So they just make it perfect, and if it's the droplet is bounce, that is fine. If not, okay, let's survive. But as you said, if you delay icing for several hours in terms of aviation, it could be enough. Or in some applications, even 1 hour is enough. Right. So if your that coating is broken in say half hour or 1 hour, it could be not a problem. So it depends on applications. Right? True. Very nice presentation. Thank you very much, and nice to know what you are doing and your team is doing.
Certainly. So let's, as usual, you ask the question in the most modest way and it goes right to the point. When I showed the morph work, you would have seen that I talked about the growth. And the reason I talked about the growth is not just because it's physical deposition, because we were worried about the interface rupture. So what we are doing is actually we are covalently linking it. In other words, if that interface were to break, it will have to fracture there. It's not going to have to delaminate. It is going to have to fracture there. It's a very important point, right? Actually, it comes with a problem because it slows us down. The growth process is slow. Rather than if you can just spray it on, it's a paint. Paint industry can work with that. And based on what we are discussing, that's not a good idea because it will, as you said, delaminate. Now, the second point about the contamination being possibly ruinous gives us hope that people like me are useful because you can have the self-cleaning behavior. The contamination prevention is what we do well with the natural surfaces, right? Now, the question is what sort of contamination and in what kind of conditions? It's a very different problem then, right? Is the contamination a dust particle? And is the dust particle simply gently sitting on the surface, or is it coming and impacting on your surface? And that's a very different set of problem. So I feel like, there is a box and we are around the periphery and we're gradually making progress. I don't know how much time it will take. I wish I could tell you, but I'm not a pessimist. I don't think you do much by being pessimist. You try to do best you can. That's what engineers do, Anyway, I hope that answers the question, but I think you're spot on as usual. The one point I'll make is, I'm very new to this, so there may be some of you who know a lot more. There's something around acoustic impedance point, something about metamaterials, and particularly mechanical metamaterials. There could be ways for you to actually use the structuring near the interface to be able to direct these pressure waves. I'm very new to this. I won't say anything more than that. Suffice it to say, we are thinking about it. So if you are interested in that, because it could potentially have implications to noise and things like that. So maybe not for the plane, but for a building that needs to sit in a harsh climate, that might actually be useful. Or, you could have this retreat in a building that sits somewhere offshore and so on and so forth. And you would still like to have a conversation and that sort of stuff. Anyway, yeah.
Sasha?
It's very interesting remark about noise. You said, because there is funny papers. It's about a rock concert on a stadium in the center of city. Right? So there is a paper, and the question is how to protect the people around.
Yeah, fair enough.
Okay, that are people who paid money and are in the stadium, they enjoy. But how about the next building? And the answer is very simple. So you need to make a trench just one around the stadium, just 1 meter deep, and fill it with something.
Right.
And that is enough, because about, I'm not sure, but about 60% of that energy from impact of your droplet, from the noise, goes along the surface, along the ground. It goes not in the waves.
Right.
Waves are not so important, actually. Okay, that waves on the surface are important. And by that range, you protect all your city. So
there you go.
all the noise goes just to the good.
That's what we do then. Oh, some people might complain. They want to hear the concert for free, and then that might complain, right?
More about that?
What the gentleman said is I studied that I've done sound as a career.
Yeah, right.
And when we do sort of outdoor concerts, you literally can break the sound up by putting the metal barriers around the concert. And what that does is it displaces what's happening. So in a similar sense of how a double slit experiment happens, it displaces all of the atoms around. So then because of that displacement, it gets filtered upwards or downwards under your own control. So we use sand and aluminium to protect outside source. So they do a similar thing called phasing in airplanes. So they put the same noise back, which is the same thing in sense, back into the plane, and then it becomes silent. So yes, in sound, that's really impressive.
Thank you. What's your name?
I'm Nathan.
Nathan. Thank you, Nathan. That's great stuff. And thank you for everything.
At least we had one presentation that you were finding interesting. That's good. I appreciate that.
There was a question. Oh, yeah. Okay.
Thanks very much for talk. It's very interesting. One question about the controlling the nucleation processes. I wonder if you can reverse it. Can you actually make it freeze more?
Can I make it?
Freezing more. Rather, you're preventing the freezing.
No, good point. Good point. We've actually had a project on this. So people tend to use nucleation promotion agents. So there are some salts, etc., like silver iodides and so on. The difficulty with it is, and so this was in the context of rapid ice formation for ice production process. The trouble that we ran into, so I think we did reasonable. I think we did reasonable with the production part. Where we ran into the problem is the ice will form, but it will get stuck onto the surface because we were messing about now. We had added this nucleation promotion agent, and that was changing the interface. So you have the double problem of, let's say, it forms on the interface, right, and then gets stuck onto it. So the thing that ultimately led to some improvement was to add this kind of nucleation promotion agent into the water itself. Now, there is a problem with that. If you're trying to create it for somebody to eat the ice or drink it, etc., you're very limited to what you can add there. So we have thought about the problem is all I will say to you.
Okay. Maybe just some kind of comment to this. It's a question about which surfaced quite soon about the melting of the permafrost in the Arctic. And I was actually quite surprised that the Alaska wants to refreeze permafrost on land. And I don't know how they're going to do it. It's a big technical question, a big upscaling question. I just wonder if the technology is ready for that or not. That's it. Application.
Yeah, but I think you're spot on. It should, let's say, in the laboratory scale, I can think of many different ways of actually promoting that. Many, not just one and two. And you replace anybody like myself who works on the icing and surface engineering, they will say the same thing. What will be probably difficult is how we're going to scale it up and all the other problems that colleagues have been talking about in terms of robustness, etc., etc. That I don't know. That we stayed with it for a couple of years or so on, and we said, okay, we can form ice and so on. You know how it is with the projects. Yeah, pleasure.
Okay, any more? No, well, thank you again.
Thank you, Frank. Thank you. Cheers.
And thank you, Sasha, for your many questions. Okay, sorry, yeah.
Thank you very much. Kind question. Thank you.
Okay, thank you. And thank you for all the participants for these 2 weeks of very nice talks about sea ice and ice in general. So we started from a very big scales of climate models and so on up to the nano scale today. So we covered most of the scales we could. And I hope you enjoyed, and yeah, hopefully we'll see some other meetings together. So, okay, thank you and have a good road home. Okay, bye-bye.